unless I confess that this is take number 2. So Unit 1, Day 3, recording it on Monday, August 14th. Graphical analysis of function. So a whole lot of words today as you look through. You're like, wow, that's a lot of stuff going on. Most of it you either already know or it's really easy to figure out. So it's very important, but it's also very intuitive. So there's some technical stuff in there, but once you understand what's going on, you're not really going to have to worry about the technical stuff. We'll worry about it when we get there. All right, we use a variety of ways to analyze and describe graphs. You're already familiar with most of these. So we're going to cruise through this first third pretty quick. Stop me if you need an explanation, though. Zeros or roots of a function are the x value where the function value is 0. Meaning you get f of x equals 0. It's the same thing as the x-intercepts. I wish we had put these like on the same line, because if y is 0, then that's a 0, or a root, or an x-intercept. Zeros, roots, x-intercepts all mean not exactly the same thing, but for our purposes, and certainly when graphing, it means the same thing. It means the y value is 0. We're looking for the x value when the y value is 0. Y-intercept, find the y value when x is 0. Equations of vertical asymptotes. So that's where x values that make the denominator 0, but that's not a whole. I think you've done this before, but we'll do a quick example here. X minus 2 divided by x minus 2 and x plus 3. So what's going on at x equals 2? If they cancel, do you remember what that makes on the graph? That makes a hole. Now the x plus 3 didn't cancel, so what's going on at x equals negative 3? Asymptote, and let's be more specific, a vertical asymptote. Is that familiar? Seen that before? Okay. Horizontal asymptotes is what happens when x goes toward positive or negative infinity. So that would have a horizontal asymptote of y equals 0, because as x gets really big, your y value is headed towards 0. It's expected that you already know how to determine all of that stuff. We'll go over them more in detail in the next unit, which is about rational functions, which is what that is. A function that's a ratio. But that's next unit. Let's doing easier stuff today. Today we're going to talk about increasing and decreasing, relative maximums, relative mins, absolute max, absolute mins, and maybe even a little bit of concavity. The big deal with increasing and decreasing is you have to read the graph left to right. Right, read a graph like you read a book, left to right. And there's one way I can do this that will intentionally mess you up, try to trick you. If I draw that graph, is that graph increasing or decreasing? What was that? Well, I've intentionally tried to fool you with that one. But if you read that graph from left to right, so ignore that arrow that's on there that's trying to trick you into saying decreasing, that is an increasing graph. Right? I mean, it's obvious why people would say decreasing, because like, look, the arrow says it's going down. Well, yes, but as you move left to right, you are increasing. So you got to read left to right. Don't be fooled by the arrows. May as well put the other tricky one on there. Let's do it this way. Oops. So that graph, increasing or decreasing? Decreasing. Right? The arrow's pointed up, but don't be fooled by the arrow. As I move left to right, that graph is decreasing. All right, relative max, this is just outlining. We'll get to the details of them in a minute. We'll get to the details in a minute. Intervals where the function is increasing or decreasing. A function is increasing on an interval I if for any two numbers a and b in I in that interval, f of b is greater than f of a if b is greater than a. What? That's a lot of words. Basically, as x gets bigger, the y's stay the same or get bigger. So as x gets bigger, the y gets bigger. It might stay the same, so there might be a spot that levels off. But that's increasing. Decreasing, I'm not even going to read all the words. It's the opposite, right? As x gets bigger, y gets smaller, so that's decreasing. Again, as long as you read your graph left to right, this isn't hard.
Is a constant function increasing and decreasing at the same time?
So by this definition, yes, which is why I don't really like this definition, but it's yes, because of how it says stay the same or get smaller. Yeah, so the question is, well, if it stays the same the whole time, is a constant function increasing and decreasing? By that definition, yes, although we would never say that. But that's a good observation. If we add this word strictly in there, we sort of get rid of the problem that Jester was pointing out. Strictly increasing means there aren't any constant spots. So you're not allowed to level off. You might be increasing at different rates and decreasing at different rates, but there's no leveling off. You are always increasing or always decreasing if that word strictly is in there. No level spots. All right, I hope this feels easy, because it should be so far. Example, a graph on the right. Well, what intervals is f increasing? Let's see. Increasing means going up as I move left to right. So increasing until we get there. Then it's decreasing, and then we're increasing from there on. Color code this to just way overkill this thing. So we're increasing from negative infinity up to 1. And then from 5 out to infinity. Now, I intentionally left off the parentheses versus bracket. What do you think? At 1, do we want to include 1 or not include 1? Good. I'm glad the people who are guessing are saying they want to include 1, and that is right. And then the same for 5. We want to include those. I guess the trick is when we say decreasing, then we're going to be decreasing from 1 to 5. And we'll include those. And for some people, it just feels weird that we included 1 in both. Because then it's like, well, are we increasing or decreasing at 1? Because you included it in the increasing interval, and you included it in the decreasing interval. So what's going on? And I think the answer is, you can't be increasing at a point. Like, you have to know like what's going on around the point to know if you're increasing or decreasing. So on the interval, 1 to 5, you're decreasing. It starts decreasing at 1. Stops increasing at 1. Straightforward? I feel like this is a pretty easy lesson so far. Try number 2. Same questions, different graph. I'll hit pause and you try number 2. So there's our increasing and decreasing intervals. Good with those? Again, as long as you're reading left to right, not a problem. All right, relative extrema. Relative meaning relative to the point's neighbors, relative to its neighbors. So a relative maximum doesn't mean you're the highest mountain in the range, but it does mean you're at the top of a hill. Might be a really tall hill, might be a small hill. But if you're at the top of a hill, you're a relative maximum. Relative minimum is kind of the same thing, except valley. You're at the bottom of a valley. Might be a deep valley, might be just a small like footprint in the earth. But if you're at the bottom, you're a relative minimum. Like relative to your neighbors, you're the minimum. A function f has a relative maximum. I don't know, I like this better. It says at x equals a. When is fine. When x equals a or at x equals a, if f changes from increasing to decreasing at x equals a. So think about what that says. We're going from increasing to decreasing at x equals a. So yeah, that makes you at the top of a hill. If you changed from going up to going down, like that's the definition of the top of a hill. Kind of the same thing for minimum. If you go from decreasing to increasing, well, that meant you were at the bottom of a valley, so that was a relative minimum. So in example number 2 above, state the values of x at which g has a relative maximum. By the way, values is maybe plural, so there might be more than one. So relative max, looking for the top of a hill. How many tops of hills do you see in that graph of g? 1, okay? These endpoints, they look like they might be relative max, but you don't know what the neighbors are doing. Or better said, you're increasing, but you don't know if you changed to decreasing. So those endpoints can't count as relative maximums or minimums. So only x equals 2 is the only maximum. How many relative minimums do we have? 2. So -4 is a minimum, and x equals 7 is a minimum. All right, now for the calculator. It's the same type question, it's just the calculator is going to help us find those points. So grab a calculator and type in 1/2 x to the 4th minus 2x cubed plus 3x minus 1. And then, as always, double check to make sure you typed it in there the right way, because your calculator is not going to make any mistakes. It's only going to be if you put the equation in wrong. I didn't want to mess with a fraction, so I just put 0.5 instead of 1/2. Okay, everybody got their graph? State the point at which h has a local maximum. All right, well, let's pause for a second here. Question 1 asks for the values of x. Question 3 asks for the point. So make sure you give the right information back. right? I mean, you're looking at the same stuff, but this wanted x values, and now we want the points. We want the x and the y. All right, local maximum. Well, I can point to it, right? It's like, hey, it's that point right there. Now, do you know how to get that point, or how to get the calculator to tell you what that point is? I was hoping someone would say that, because it's not right. Don't use trace, okay? Trace gets you close. Like, I don't know, maybe it's 0.851.
Maximum.
But I don't know. Like, I don't know. So you go to second calc. If you make it that far, you can make it from there, because then it's like, oh, well, there's an option for maximum. Second calc. And then maximum. And it'll walk you through the steps you need to do from there. Second calc maximum. And then it prompts you for a left bound. That means get to the left of the maximum. So come to the left a little bit, press enter. Right bound means get to the right of the maximum. So scroll over till you're past the maximum. Press enter. Yes, you can just press enter again, or you can try to help your calculator out and go find the as best you can. So our maximum is, the x value is 0.832. By the way, always 3 decimals, because that's what the AP test wants. 0.832, 0.584. And we're not really setting up to take the AP PreCal test. It's the first year of it this year. But for AP Calculus next year, we just want to get in the habit of 3 decimal points. Or second trace, maybe it's a better way to say it. All right, you try the same thing. Well, actually, need to back up. How many local minimums are there? 2. So you have to do the same thing twice, but with minimums. So I'm going to press pause and give you time to find those. There's our 2 local minimums. Okay, just using the calculator, really. How did I what? A function has a relative maximum of f of c if there's an interval containing c on which f of c is a maximum. That's almost like circular definition kind of thing. Same thing with a minimum. I would not worry about those 2 lines. That's kind of weird. Relative extrema are the same thing as local extrema. Maybe that's a better word. Like, locally, I'm at the top of my mountain, even though there's a bigger mountain over there and a smaller mountain over there. Locally, I'm at the top of a mountain. So you can have a local min or a local max. Absolute extrema. Well, this is maybe what you think it means. The absolute maximum value of a function and the absolute minimum value of the function are also called the absolute extrema, or global extrema. And here's the technical definition. F of c is the absolute max when f of c is greater than or equal to all the other, when it's the highest point. Right? So that's the less technical definition. The highest point and the lowest point. Sometimes we're given an interval in which to find the absolute extrema. Other times we need to examine the full domain. So sometimes I'll just say, hey, look between 1 and 7. Just look in that little window and tell me what the max is. Other times I'll just say, hey, just here's the whole function. Where's the max? So, make sure you read the whole question and understand what's being asked. It's important to know that the absolute maximum of a function and the absolute minimum of a function are actual values of the function. Maybe that seems dumb, but we'll look at an example. These are y values of the function. They have to be from the function. Here's an example. So what's the absolute maximum of that function? It's kind of a trick question. There is none. Right? It's not 2 because 2 is a whole, and if it wants to be the absolute max of a function, it has to be on the function or part of the function. 2 doesn't count. 2 is a whole, so you can't use 2. And then you're thinking, well, how about 1.9? Well, 1.99 or 1.99999. And so there is no absolute max for that function. So that's kind of weird. Even though everything is less than 2, 2 is not the absolute max because it has to be part of the function. All right, examples. This calculator. This is the same equation we were just looking at. So you should have it typed in already. Find the absolute minimum if it exists. Well, I got lucky. Mine's still up there. Right? There's 2 local minimums, but the absolute minimum is the lower one. Be careful about what it asks. The absolute minimum value. So is that my x or my y? That's the y. The value of h is the y value. Negative 5.772. What about the absolute maximum value of h? What do you think? Is it the top of this hill right here? Nope, because there's maximums that are bigger than that. It doesn't have an absolute max. Because it just goes off the page. You could say it goes to infinity. That would be correct, but it does not have a maximum. Find the absolute maximum on the interval from 1.5 to 3. So, 1.5 to 3. So I probably need to check 1.5 and I think I'm going to have to check my endpoints here. H of negative 1.5, H of 3, and I already know there's a local max at 0.584. But I need to check my endpoints here. Second calc again, or second trace. And I want a value this time. Rather than, so I could go in and plug in negative 1.5 into that equation, and that would be annoying. So I can go second trace value and just type in negative 1.5, and it plugs it in for me. 3.781. Second trace. Now I want a value, and then you just type in whatever x value you like. So at 3, my y is negative 5.5. So my absolute max on that interval is 3.781. Now that's not a local max, but that's okay. It's the absolute max on that interval. All right, the next part, we can skip the next example, and I think we're going to skip concavity. We'll just say, because this is more of a calculus thing, concave up. Concavity is like how it's bold. You can be bold up or bold down. So all of these are concave up. These first three, we're just going to breeze through this here. Concave up, concave down. Would it hold water or would it not hold water? Is another way to say it. Although that's tricky too, because these two examples, it's like, would that hold water? You're like, well, not really, because it would just squirt out the ends. But it's bowled up, so that's concave up. Those would definitely not hold water, so they're concave down. We're not going to do much with concavity this year. That is definitely a calculus thing, so you don't have to really worry about that. All right, this is worksheet 3. It's today's assignment, and remember that due on block day is worksheet 1 through 3. Answers are posted. I will happily answer questions tomorrow.